the guy Dimitri as well. So thank you very much for coming. We're going to talk about my personal project, which is a Python Astrodynamics library. This is what we're going to review. So first, I'm going to do a very quick introduction to what this orbital mechanics stuff is, just for people that don't know anything about it, to set some context. Then we're going to describe what poliastro is. I'm going to give a couple of examples of what it can do. And then we're going to review some of the challenges that I faced when developing this project, which are validation, having a good performance, achieving a nice API at the same time, and building a good community around it. And then we're going to jump to the conclusions, and I'm going to invite you to contribute. First, some words about me. I'm an aerospace engineer by background. I'm a software developer in Satellogic. It's a satellite company that is launching a constellation of low Earth observation satellites that is capturing the whole Earth. And as well, I'm very involved in the Python community. So I am the chair of the Python Spain non-profit. So we organize the Python conference every year, and we do give support to the local communities, and etc. Also, the vice chair is here with me in the audience, so you have like the half of the board of directors of Python Spain here in PiterPy. I'm a free software advocate. I really want to push using free software for scientific and engineering purposes. This is my small contribution to it. And I'm also a hard rock lover, just in case. And I code like a girl, by the way. So please follow me on GitHub. So a quick introduction to orbital mechanics. So orbital mechanics is a branch of physics that studies the motion of human-made objects in space. So just to give a very quick introduction of why do objects orbit in the first place, this is a mental experiment that Newton designed like 400 years ago. So imagine that you are in the top of a mountain here, and you're like launching a cannonball, and the stronger that you launch the cannonball, the further it goes, and you reach a point where the cannonball starts to go so far that the surface itself of the Earth starts curving downwards around itself. So there's a velocity, which is called the orbital velocity, where you never hit the ground, and you keep on falling and falling forever. So this is what we call reach the orbit. Of course, if you increase the velocity even more, then you get a higher and higher orbit, and there are many things you can do. But the basic fundamentals of how this works is just this. So if it's so simple, then what's the point, right? So first of all, it's very difficult to measure correctly, because these objects are very small compared to the size of the whole planet, as you can imagine. But you need precisions in the order of the centimeters in some applications. So you have to have very accurate methods to measure the position and the velocity of this kind of satellites. Also, there are many perturbations, because the easy model, where the Earth is a point and the equations are very simple and etc., it's very easy to solve. But this is never the case, because the Earth is not a point, it's like a pear, something like that. It's a very ugly sphere. There's also the influence of the atmosphere, so it's slowing down the satellites that are in a very low Earth orbit. And you even have the pressure from the sun itself, because the radiation from the sun is like changing the orbit itself. So you have to take so many things into account that are very difficult to have them all together. So it's quite intensive in terms of computational resources if you want to do a proper analysis. And last thing, if you lose contact with the satellite, well, it's much worse than a needle in a haystack, because finding something in space without knowing where it is, it's an impossible task. I wanted to show a video to give an example of the kind of problems in orbital mechanics that are more appealing to me. This is the trajectory of a mission that we launched in the European Space Agency to reach a comet 67P, or Churyumov-Gerasimenko, as it's called. It was some years ago, and as you can see here, it was launched from the Earth like in 2004, and after giving a full orbit around the Sun, then we do what we call a gravity assist. So we try to pass very close to the Earth without hitting it to try to change a little bit the orbit here. So now we're in a different orbit, and we use that impulse to pass very close to Mars and do a very similar maneuver. So this game goes on and on with the years. We do another Earth gravity assist. Now we use this moment to visit some asteroid that is around. And this is like very, very complex to optimize because you have to take into account all the possible combinations that you have with all these planets. And then the last gravity assist throws us very, very far away. This right here is the orbit of Jupiter, and this is the orbit of the comet that we want to visit. So remember that we launched in 2004, and now in 2012 probably, 2014, sorry. Now we're starting to approach the comet and reach exactly that point. So it's a mission that lasts for 10 years, and it's so complicated, but at the same time, I find it so very beautiful. Okay, thank you. So now, what is poliastro? Well, poliastro is a Python library for astrodynamics or mechanical mechanics, whatever you call it, focused on interactivity and ease of use, correctness, interactive visualization, and etc. So it contains lots of algorithms that are very computationally intensive, but it's all written in Python. We will talk about this later on. It has a permissive license. It handles for you physical units, astronomical time scales, so the astronomical version of time zones. And you can check the documentation here, and we release a new version every 6 months or so. And also we do conference-driven development. So we find all the bugs while preparing the talks for the conferences, like this one. If you go to the issue list, you will see some recent ones from last night. So this is a brief history of the project. I started this in 2013 because in university I was given the task of analyzing an orbit around Venus and some perturbations. So I started with some FORTRAN and MATLAB code. I didn't have a MATLAB license. I never had, so I had to run it with Octave, it's like the GNU version. And it was working well in my computer. It was known to work nowhere else. So I was a bit frustrated with this. So in 2015, I replaced all the FORTRAN part with pure Python using numba. I'm going to talk about this later. I presented these results in the European Space Agency, and I managed to get more or less the same order of magnitude of performance. It was, of course, slower than FORTRAN, but not much slower. So I was pretty happy with it, and now you can install it on Windows without getting insane in the process. Then I added some algorithms, and for 2 years now we've been participating in Google Summer of Code, in the European Space Agency Summer of Code, so we were getting like students getting some work done during the summer. So this is a glimpse of what you can do with poliastro. So you can do orbit plotting. Here you specify the position and the velocity, and you say that this is an orbit around the Earth in the moment that is now. If you just display this, it gives you like some information about the orbit itself. And then you can just visualize like a very schematic plot of what it looks like. You can also do three-dimensional plot. This took me a lot of time to get right because matplotlib three-dimensional capabilities are very, very limited. And the 3D scientific visualization landscape in Python is not that simple. There are lots of data science-oriented visualization packages, but not that many scientific ones. So the alternative was using VTK, Mayavi, or stuff like that. But in 2013, it was very problematic. And now I discovered Plotly, and I'm super in love with it. I recommend you to check it out. We can also read orbit from external data. So here you have, for example, the solar system. So you have Mercury, Venus, Earth, and Mars, the inner solar system. And we can read some orbits for small bodies, comets, asteroids, and etc. So here we have Halley's Comet as it was seen in 1835, because there are like many observations of it. And also the Florence asteroid that was passing right next to the Earth in September last year. So here you have like a very simple visualization of it in like 6 lines of code, which I think it's a very good thing to do. Here you can see all the observations of the Halley satellite. Here there is lots of science going on, because to plot these orbits correctly, we have to do like some magic in the numerical side to be like very optimal in what points do we sample and etc. But we are hiding all that complexity for the user. So now let's talk about the challenges. And the first one that I have is the validation. So unit testing a function with clear expectations is very easy. Like if you expect a function to return an object like this, and this object should have this state and these properties and etc., then you test for that, and that's right. It can get more or less complicated, but more or less most people know how to do it. But what about numerical algorithms? What are my expectations on this? So I have a very simple example of this, on how to do it the very, very wrong way. So imagine that you have to write this function here. So the sine of x divided by x, a very simple mathematical function. And now how do you unit test this thing? So there's an option that says, OK, so I'm going to import PyTest. And now I'm going to copy paste this formula here in the test. And I'm going to test this function for 0, 1, and 10. And that's it. And I could even be worse and not test here by 0, because here I will have a beautiful division by 0 and nothing is going to work. And this is wrong on many levels, but the first level is that you never ever have to do floating point arithmetic comparisons. I never get tired of putting this example here, but as you might know, 0.1 plus 0.2 is not equal to 0.3, but 0.2 plus 0.3 is equal to 0.5. Whenever I teach Python to undergraduates or whatever, they always get amazed by this fact over here, and they wonder if Python is broken, if they can buy some software that does it correctly and whatever. But this is an implementation of the floating point arithmetic in every single programming language out there. So it's a problem that we have to avoid in some other ways. So the thing is that we should compare this instead of, well, first do floating point arithmetic right, that's the thing. And then we should, in my opinion, compare the output to some external sources where we know that this data is correct. For example, if I have some mathematical handbook where I know the value of the function, or if I have some paper that gives this result because they already analyzed the algorithm for some specific case, and etc. So this is more similar to what I think we should do when testing like numerical algorithms. So here there is a book where there is some textbook assignment, and then I copy the input data and the expected output, which is copied from the book, and then I run my algorithm and check that my output is equal to the output from the book. And this is a better way to validate this algorithm. Here I have to specify some tolerance because I will never be exactly equal to the result. And also I will have to try to investigate where this uncertainty comes from, because it might be that the book didn't provide enough decimal places. This is very typical. Or many other things. I will talk about this right now. But still, this has some limitations, and I don't have perfect answers for some of these. So for example, how much precision do you ask for? That's a question that you might not be interested in investing a lot of time in, but it's worth asking at least. Then what happens if your results don't match? Is it an error in your side? Or maybe the paper where you're copying the algorithm from, it has some typo or something. Because good luck trying to contact the authors of the paper or the book. Then, if the precision changes, it's because I'm having bad data, because I have broken my algorithms in some way. And also, how do you track improvements? Because if you go back to the test, I'm doing an assert here. So if the assert fails, I'm going to have a red flag. But imagine that I improve the algorithm and I go from 1 to the minus 5 precision to 1 to the minus 10. I'm never going to notice this because the assertion is not going to inform me. So I still don't have like an automated tool to track this kind of thing. And then talking about the external data stuff, this is a summary. So nobody cares. Those who care don't share it. Those who share it do it with 1 decimal place, and this is true story. I've seen it so many times. Those who share it with 16 decimal places don't describe how it was obtained. Release the source code of the software, please. Scientists of the world. And those who release the software make it impossible to compile in, I don't know, recent hardware. So it's a very, very sad landscape when you try to validate numerical algorithms, and you just have to cope with it. Another option is to use commercial software. So for example, there's, of course, commercial off-the-shelf products to do orbital analysis for companies and etc., very professional. So I could say, okay, so I'm going to run this analysis with this software, and then I'm going to try to check if my output is the same. But it's complicated because sometimes this professional software is so advanced and so powerful that reproducing these simple cases that you want to validate, it's very, very difficult. And also, well, it's commercial to begin with, so you have to buy it. Maybe it doesn't work in Linux, so you need like a virtual machine and blah, blah, blah. So everything can get very, very messy. I don't have a perfect answer for this. As I said, I'm open to suggestions here. If you're really interested, you can check out my final master thesis when I did some work regarding validation of these algorithms. So now the second challenge is, how do I get good performance and a nice API in the library? Because I want to be as user-friendly as possible with Poliastro and try to democratize, in a way, the way you use and you analyze orbits. So I want to protect the user from very common mistakes, such as mixing meters and kilometers, for example. And you might think this is not very common, but I copied this screenshot from a news outlet from 1999, which talks about Mars Climate Orbiter, which is a mission that did what we call, in technical terms, a lithobraking, which is decelerating in the surface of Mars very, very fast, or crashing. And it did because one of the contractors was using the imperial system and the other one was using the metric system. And it's as ugly as it sounds. They lost billions of dollars with this. So you don't want that to happen to anybody, of course. And there are more errors that you can have, because you can have like bad use of reference frames. There are many stupid things that can bite you. But performance comes at a price, in the case of Python especially, because yes, Python is slow, and the points where we don't notice is because the underlying code is compiled in reality. Because if we say, yeah, you can use NumPy for everything, and you're not going to notice that Python is slow. But NumPy is C code underneath. And when you start to have, for example, this units code that checks, okay, so convert me this to meters, from meters to kilometers. And now you have to check the unit, the AstroPy code that does this, does lots of introspection, is instance calls that are super slow for some cases. So in the end, all these high-level abstractions have a very high cost in terms of performance in Python. So how to accelerate the code? And this is more or less the trip that I did to try to accelerate this. So first, I tried to do vectorization, so using NumPy for everything. NumPy has lots of high-level functions to manipulate arrays. So if you rewrite your algorithm in terms of this function, then these functions, then it's going to be much faster. But the problem with this is that some algorithms cannot be vectorized. Anything that is not in terms of arrays or matrices or whatever, it's very difficult to vectorize, and especially like sequential problems where you need to keep the state in the following steps, they're very difficult to vectorize, if at all. So, and also, even if you can vectorize, sometimes the code is so difficult to read that you don't understand it 6 months later. And this happened to me, and this is a screenshot from a real commit where I reverted some vectorization because I could not figure out what the code was doing, like 6 months after doing it. Then there's Seitan, for example, and Seitan is a great project. It's very mature and many people use it. It's essentially like mixing C and Python in the same language in a gradual way, so you can add like more C-like information to your Python code and it gets faster. But I have some personal problems with it. First, that I don't know any C. This is a limitation of me. So like using Seitan is going to be much more difficult for me to get right. Also, I wanted Polyester to be super easy to install. And in 2013, this involved using Conda for everything. Now we have wheels and the ecosystem is much more mature, but it was not the case back then, especially in Windows, where I still need conda for some packages. Then the native debugger of Seitan is broken, and the core developers don't seem to care too much about it. I have like a repository where I tried to configure the debugger to work properly, and also I wrote a message to the mailing list, and nobody's answering me. So I don't know what to do with this. Like, you can debug on the C side, but you cannot debug the Seitan code itself. So for me, this is a big limitation, especially while I'm learning, you know. And also, I really just don't want to worry about the bound text of the arrays and all these things. You know, I want the code to be as high level as possible. So I'm not using it, but also I don't have lots of experience using it. So I really don't have like a very well-informed opinion on this. Then there's PyPy. Who knows PyPy here? Okay, PyPy, it's a really interesting project. It's an alternative Python implementation, so no like C Python, the canonical one that everybody uses, but a different one. I really, really want to use it, but there are lots of obstacles in the way. So for example, the documentation is a bit poor in my taste. The changelog is difficult to figure out sometimes because there's like 2 separate versions, but they do the release at the same time. It's a bit messy. Also, the mainstream community doesn't seem to care a lot. I saw a video from Guido van Rossum in some PyCon doing like snarky comments about nobody using it in production, and I think it's not really nice. Also, supporting conda is half broken. You don't have like the opportunity to separate the packages and to only use PyPy packages or etc. It has some incompatibilities with many Linux 1 wheels, which is the wheel format that we use nowadays. And there's a second iteration going on, Many Linux 2010, based on a more modern CentOS version, I think. But it needs some love. It's almost there, but the people involved in the pull request need to like do the final push. So until then, we cannot do much. So I'm using numba. I'm going to run a little bit, but numba is a Python to LLVM just-in-time compiler. So you take your code and you compile it on the fly, and it's super fast. If you are using numerical code, you don't have to touch anything because it works out of the box, but it won't accelerate like high-level Python structures, complicated objects, introspection calls, and stuff like that. And also, now I have a very big issue with it, that is that you cannot pass a function as an argument and accelerate that code. And for me, that harms all the whole point of reusability. So here's an example of how to use it. You have like this function to do some Monte Carlo sampling to find the digits of pi. This is a very typical example of Monte Carlo. And if you run this with Python with 1 million samples, for example, it's going to take about, it's going to take about like 0.4 seconds, more or less. So if you can take this code and just use this ENG function on it, then you call the function again. The first time it's going to vectorize everything and see what are the types and etc. But then the following times is going to be 30 times faster. And this is not really very, very impressive. But if you have like lots of nested loops, like for loops and etc., which is very typical for image processing, for example, then the speedups are huge. And for us, this has been a deal breaker. Also, debugging is not always as easy as it could be because the error messages are not very useful. This has been improving a lot lately. And now you will have like an annotation functionality where you can display here like what's the point of the code where things are getting slower and etc. So this is the solution we adopted in Poliastro. We have a nice high-level API that accepts units everywhere and that does the right thing for you. And then here you have the dangerous algorithms where you can break things or shoot yourself in the foot. But all this part is accelerated with numba, so it's really, really fast. And this is like a decent trade-off that we found. This is more or less how it looks like. So we have this function here with some validation of the units. So this has to be an angle, and this has to be a dimensionless quantity. And here I'm computing like the value of everything in radians and just the value. Then computing the fast function, which is accelerated with numba, and then converting back to a unit. So you get like this sandwich structure, and it's working really, really well for us. And then, of course, what you cannot measure, you cannot improve. This is Airspeed Velocity, which is a tool to do like performance benchmarks, and it's really, really advanced. These are some benchmarks that we've been performing on some specific example, and it helped us a lot to detect a regression that we had here, and we fixed that in following versions of the software. And by the way, now that we see this, these are the benchmarks in my laptop, and these are the benchmarks in a server that I bought. So please, don't do benchmarking in your laptop while you are, I don't know, listening to Spotify or Netflix or whatever, because it's going to have a lot of noise. And then community building, only 2 words about this. There's a quote by John Hunter, the original author of Matplotlib, that passed away some years ago, that says, "I believe the choice of license is an important one, and I advocate for a permissive license, because the most important commodity of open source is users." And I totally agree with this vision. I know that some people do not agree, and I also don't claim that it's valid for all the cases, but I really, really like the permissive licenses and the attitude and the things that they encourage. So how to contribute to Poliastro? I have a surprise for you. You don't have to know anything about Astrodynamics or anything, because I have lots of bugs with things that are not related to it, because I have problems with the plotting, with the tests, with the continuous integration, with the documentation, with the infrastructure, with the object designs, because I don't have like a training in computer science. So I have lots of questions and lots of things that you can contribute on. We can publish a success story if you do something cool, by the way. And as long as it fits like the focus and the scope of the project, I will be really, really happy to talk. So this was everything that I got. You can see the slides right here. You can join the Poliastro chat, which is in Riot, an open platform. It's like a modern IRC. And you can follow me on Twitter. I do not know how to pronounce this, but I know that it says thank you very much.
Thank you. Now we have time for Q&A, of course.
Okay, so the most interesting in this problem when it comes to testing numerics. So usually you have some numerics. Usually you don't have some ground truth. So okay, unless you create another algorithm, and also usually you have some approximations, or other numerical precision, or other tricks or stuff. And you said that it's a difficult problem, but how do you approach that?
Well, for me, the worst thing is when you don't have ground truth, and this happens a lot of times. Like when you're doing something really complicated, I am not in the academic world, but if I ever do like a PhD on orbital analysis or something like that, I know that I'm going to find problems that nobody has done before, so you won't have ground truth for that. I think in that case, the minimum that we have to do is to have like a regression test. So test our algorithm, see the output, and have some assert somewhere that say, okay, so this was my result 1 month ago, and if it changes, I'm going to notice, and I'm going to wonder why. And I think that's the only thing we can do in these cases.
And then how to do so? Because usually, well, when you run some tests, you run it within a single commit, right? Or how do you do so to compare other commits?
Hey, are you concerned about the performance, the slowness of the tests?
Well, like also, but most my biggest concern if it's correct, in the sense that if there's no some big mistake.
Yeah, I have an automated pipeline like any other GitHub project has with Circle CI and Travis and etc. So I run all the tests for every single commit. Also, I have like some slow tests that do like very hardcore numerical stuff, and I run them like from time to time in my computer, but they're always run online. So like I'm checking every single time if I'm breaking something.
Okay.
Ooh.
You called your presentation, well, catching the asteroid or something like that. So is your Polyester program capable in terms of accuracy to calculate, well, some problematic cases like the Apophis asteroid and its possible impacts?
Yeah, like The algorithms that we're using in Poliastro, they are the algorithms that you would expect in any professional program, so they are complete in that sense. The uncertainty comes from the input data, because, for example, sometimes you don't know like the position of the asteroid, and if the European Space Agency gives me like all their observation and everything, then I could try to fit that and get a result that is as good as they can produce, maybe in more time, and because also I will need to know like which perturbations are they taking into account. So there are lots of things that are like around the problem itself that you have to consider to do a proper analysis. But from the algorithmic point of view, Poliastro can produce a result that is as good as anybody else.
And is it suitable for long-term modeling, like for billions of years in the averaging tasks and so on?
Modeling in billions of years has the problem that you're always doing like an estimation. For example, for modeling like galaxies and stuff like that, there's another package that it's called, I forgot the name, but it's a package for galactic dynamics by Gala or something like that, or Gala from one of the AstroPy core committers. And it uses essentially like very similar algorithms, but it's more suited to this kind of analysis. Simulating a spacecraft for months or even weeks, it's a guarantee that you're going to have a wrong result, because you never know all the uncertainties and all the input data for sure. So in real life, you are all the time like redoing the observations and correcting the data and so on.
Thank you.
Hi. Well, first, great talk.
Thank you.
Then I had a kind of double question for you. So I wonder why did you choose Python when you decided to move to Python? And then the main part of this question is, in the history of Poliastro, have you ever thought like, oh, I wish I had chosen this other language because it would have been better?
Well, it's a very good question. I chose Python. Remember that this was 2013. I think Python is and was the way to go for scientific software that in a way had to replace like MATLAB scripts and stuff like that. I come from an engineering background, as I said, and around me everybody was using, well, a wide range of tools like Excel, Excel macros, MATLAB, more Excel. So I really wanted to produce something that was better and also accessible to anybody. I fell in love with Mathematica in my first year of university. I think it's a very, very good tool, but it's very expensive as well. And it's not easy to share the results with people that don't have it. The guy that won the Nobel Prize of Economics this year, Paul Romer, the former director of the World Bank, has a very nice article on how he switched from Mathematica to Python because he wanted to share the results with everybody. And it was kind of the same reason. And also it was a very popular language, very easy to learn, and still today, it's getting more and more popular. So for me, it's a guarantee that, it's very difficult to get contributors for this project because people feel intimidated by the equations and everything. So I think that if I ever get contributors from outside, they're going to know Python for sure. So for me, staying in Python it's a good thing. There's another guy doing the same thing in Julia, and I think Julia is a very interesting language that might challenge Python in the scientific world in the near future. But I don't know what's going to happen. Maybe sometime I will have to rewrite the whole thing in Julia or migrate, I don't know. For the moment, I'm staying in Python.
Thanks. More questions?
Thank you for your talk. It's maybe a little bit off topic. You said about time zones in space.
Yeah.
Can you tell more about it? Why it appears in space?
Well, time zones in space, first of all, time zones on Earth is not as, it's much more complicated than people think because, for example, what's the time zone in the North Pole? Because if you are rotating like very close to the pole. In space, we normally use UTC, which is like the universal scale, but there are lots of very, very small details in the time scale that you use because depending on how you measure it, if you use like the atomic clock scale, or if you use a scale that takes into account the relativity or not. So there are like a family of timescales that you can use, and they differ in nanoseconds. So normal people don't care about it, and I'm glad that it's the case. But when you need like very precise applications, you have to be very sure of what timescale are you using. And I have lots of problems in Poliastro because people take them for granted, and they're like implicit. So sometimes you don't know which one are they using. So if you remove the relativity or you add the relativity when it shouldn't be there, you get results that are off by hundreds of meters in the orbit, doing some analysis. So it's a really, really complicated topic. It's not exactly time zones, but it's similar in that respect. And of course, leap seconds. Everybody loves them.
Thanks. More questions? The last one.
So thank you for the talk as well. And also I wanted to ask you about the plotting and general like approximation of the flight of something. And
general approximation of what, sorry?
So the trajectory.
Yes.
So you were talking about the objects that have the like constant velocity, but what about like something that changes this continuously over time, like I don't know, some spacecraft with thrust, or I don't know, something like this.
Okay.
Yeah.
Yeah, having an object that has constant velocity in magnitude is very, very difficult, because for that it has to be like a perfect circular orbit. It's going to change the direction anyway.
Yeah.
And regarding things where you can actively change the velocity, such as you said, a thrust or whatever, I don't have like a figure here, but this summer of code, a Russian guy was porting some algorithms that I did from my master project to Poliastro. So now you can have like your own guidance law. So you can say, okay, so apply some thrust aligned with the velocity for some time, or do some maneuver that changes the inclination of the orbit and the size of the orbit at the same time. And I have very, very interesting plots in the documentation. And that particular thing, I think it's the only software tool that it's open source that allows you to do it.
Yeah. That's very cool. Thank you.
Okay, I think now it's time for you to pick the best question from your perspective and give this.
Thank you. So, best question. There was the thrust thing, time zones, YPython. For you. So the asteroids and the trajectories. Please, an applause.
So